So what is this? This is 21st. So exams or exam grades. And for that matter, James, I got your email. I completely forgot to respond. Yeah, so the homeworks, if you're missing a homework, I'll let you know. I just didn't upload the grades yet. I apologize for that. I have to do that. So if you don't see by the end of the day that your grade has been posted, let me know. But my plan is to finish putting all the grades in today. I know I said I would do that, and I didn't yet. But it's not that I don't like you guys. It's just that, like, I'm trying to adapt to this new world where you guys need to see your grades all the time. But of course you want to see them, I guess. You know. Anyhow, I'll post solutions to the exam. And then we'll go from there. Don't forget, next week's the last week. So, you know, we'll have class this week and next week. And then we'll, you know, feel free if you want to schedule any Zoom appointments if you have questions or whatever, particularly once you see your grades. And if you have concerns on all that stuff, you got to let me know. I will say some of you are missing assignments. So please, if you haven't submitted assignments yet, please do. I don't care if they're late. Better late than never. So if you're missing assignments, please get them in, and I would appreciate that for my sake and to learn from you guys, and also for your own sake. So please submit any missing work, and then we'll begin. Does anybody have a particular question about anything? Cool. So if I'm going to pull up from my own self our Canvas page just to make sure all that, yeah, so it's updated with the lecture notes and up from last week. Good. All right, so that's good. All right, cool. So we're on to a new topic today. And so this is going to be fun time. So let's try to motivate our next topic. So oh boy, hold on, guys. Got screaming. So so what do we want to do? We want to motivate our next topic, which is going to seem sort of out of sort of out of nowhere when you consider with what we've been doing as far as all these integrals. But I promise you there is a connection. It's just going to take a moment to get to it. So so here we go. So let's play a game. So the first thing I want us to do is I want to stand let's say 1 meter. I don't know. Doesn't matter what union. From any wall. All right, and so here's what we want to do. Stand 1 meter from any wall, and then the second thing you're going to do is cut your difference in half. So that might not be clear. And then repeat forever. And then ask yourself, do you ever touch the wall? So let's kind of draw a picture of this. Let's say we have the floor here. Here's you. Here's the wall. And of course, we are telling you that you are 1 meter from the wall. This is where you start. And so then what you're going to do is you're going to cut that distance in half. You're then going to be 1/2 meter from the wall. And then you're going to repeat. So you take half of that. So what's half of a half? Well, that's 1/4. And then if you repeat that again, what's half of that? And then what's half of that, etc. And so the question is, do you ever touch the wall? And then another question that is sort of connected with that. How far do you travel? So these are more rhetorical. Well, the first question about do you ever touch the wall, that's rhetorical. But it's something that you should ponder because it's a very interesting question that really messes with our mental. First off, can you play this game forever? And the answer is no, because you'll die at some point. Not to be sad, but but even if your friend takes over from where you left off when you pass away, will they ever finish the game? And the answer is no. Because if you follow the rules and you keep taking half your distance, you can't ever be done. Yet we know if we actually try to do this, after a few steps, we'll be done because we physically are going to hit the wall. And the thing is why are we physically going to hit the wall? Because our size relative to, half of whatever we're at is too big. So eventually a better way of saying that is that after so many steps in this game, it will be physically impossible for you to go half the distance that remains because you won't be able to do it. It will be too small. And so we can look at this in another way too as well. If we want to think about our distance traveled, what is our distance? Well, the first thing we go is we go 1/2. Right? And then we go 1/4. And then we go 1/8. And then we go 1/16, because I keep taking half of my previous distance, and then 1/32, and then 1/64. And then if you want to keep getting 1/128. And the idea is that this process continues indefinitely. Now, here's the thing. It just like your intuition tells you, if you physically try to play this game, eventually you're going to hit the wall. But at some point in you hitting the wall, you're cheating, and not like you're cheating on purpose. It's just that you can't play the game by the rules anymore. In a similar fashion, if I go to a calculator, let's say I'll go to Google. So let's go and let me share this with you. So if I just go to a calculator and take 1/2 plus 1/4 plus 1/8 plus 1/16, let me just do the first 4 terms. If I add them up, oh my God, they're showing away the trick. I just want the calculator. You cheater. You cheater. Just give me the calculator. There we go. So what I want to do is I just want to add these things up. So if I take 1, or excuse me, not 1. If I take 1/2 plus, no. All right, we'll do it the old. We're going the Wolfram. Google's letting me down here. So the point I'm trying to make is everybody seeing Wolfram right now? Yeah, you're seeing it. So what you'll notice is if I add the first 4 terms, if I play the game 4 times, then I will have traveled roughly 0.979 meters. And then if I play the game a 5th time, I will have traveled, we did something wrong. Oh, that should be an 1/8. Excuse me. So let me repeat that again. If I play the game 5 times, I will travel 0.96 meters. If I play it 6 times, I will have traveled now 0.98 meters. If I keep playing, play it again, I will now have traveled 0.99 meters. And then what's 128 times 2? Well, that's 1 divided by 256. So if I do it another time, I get 0.99 meters that I've traveled. And so we can sit here and play this game, and what's going to happen is every time I add the next term in the pattern, I'm going to get something like 0.999, and then 0.99999, 0.99999. Just like our intuition tells us that eventually when we try to do it physically, we're going to hit the door. So, or hit the wall, I guess I should say. And so what we need to do is the following, and let's be clear of what I'm trying to say here. So let's play a different game now. Whoop. So what does our intuition tell us? We eventually hit the door. Because at some point, we can't follow the rules anymore. And then that means that somehow, some way, we expect 1/2 plus 1/4 plus 1/8 plus 1/16, this pattern, we expect it to equal 1. The problem is as of right now, this has no meaning. Yet. So what do I mean by that? Well, I mean the following. I mean, we have a definition of what it means to add 2 numbers, 3 numbers, 4 numbers, but we don't have a definition of what it means to add infinitely many numbers. So while that has no meaning, our intuition says we should define this thing so that it equals 1. Now, perhaps you're a skeptic and you're going to say, okay, well, whatever, O'Grady, you're just making things up now. Okay, well, let's look at this same sort of mathematical thing from a different perspective. Let's look at it geometrically. So imagine now that I take a square. So imagine I have a square of side 1 and 1. So the area of this square equals 1 times 1, which is 1. What I want to do now is I want to chop this square up or think about it in a different way. So what I'm going to do is I'm going to take a different color. Let's take red. And now I'm going to take this square and I'm going to cut it in half. And so what do we know from elementary geometry is that if the whole area is 1, then this piece must have area of a half. And then I'm going to take another line and I'm going to take this remaining piece and put it in half. And if I do that, that means that this piece of the square has to have area of a quarter. And then I'll repeat this process. I'll cut this quarter square in half. And then that means that this piece has to have an area of 1/8. And then I'll play the game again. And this little square has to have area 1/16. And so what's happening now is I can continue to play this game forever and ever, theoretically. But as you're seeing, it's really becoming difficult for me to do it with this pen on this whiteboard. Because what's happening is it's now too difficult or it's becoming increasingly difficult for me to properly label the area of each piece. However, if we decide we're going to chop the square up in this sort of systematic way, we also get that the area has to equal 1/2 plus 1/4 plus 1/8 plus 1/16, and then that pattern shows up again. So once again, that's ugly. So once again, what we have is we have this sort of infinite sum. So in two different sort of scenarios, we've arrived using our intuition at something that I'm calling an infinite sum. Why am I calling it why am I calling it an infinite sum? Well, I'm calling it that because theoretically I can keep chopping the square up. The problem is I'd have to go get a microscope and I'd have to get smaller instruments and zoom in on that little tiny corner to keep playing the game. However, theoretically I can keep doing it. And since the total area of the square is 1, then the sum of all those pieces has to add up to 1. At least our intuition tells us that. Now, this isn't the only place these kinds of sums have shown up. So you've seen these things in other places, even as far back as when you were a young student in school, although you probably didn't think of it this way, but you did. And so let's think about this. When you were a kid in school, you were, oh boy, yeah, Ricky wants something. When you were a kid in school, you learned how to take a number like 1/3 and write it as a decimal. And what you would do is you would notice that this is 0.333, and then usually what you learn in school is they say, well, this pattern's the same forever, so you put like a bar over this. Something like that, right? Or maybe you had teachers that told you to write it like this with an ellipse to tell you that the pattern goes on forever and ever. But the question is, what does this really mean? You know, if you go to a calculator and you take 1 divided by 3, it's going to spit out 0.333. But what does that mean? How are we really supposed to interpret it? Well, the interpretation that you are usually taught as a student in school, but it's never really made concrete or solidified, is that you think of it as place values. And you might have thought of this as like tenths and hundredths and thousandths. But what does that really mean? Well, one way we can interpret this is that 0.333 ... What does this mean? Well, this should mean 3/10 plus 3/100 plus 3/1000. This is in agreement with what you learned as a student in elementary or middle school. And so this pattern continues forever and ever and ever. And so once again, an infinite sum, whatever that is, whatever. I'm calling it an infinite sum because it's not a finite number of things we're adding together. That ellipsis at the end is telling you, the reader, that that pattern continues forever. Forever. Does anybody have a question or a comment about any of this? Okay, so what do these 3 examples suggest? So what we need is a precise definition. So we need a precise definition of it. That is, how do we define a sub 1 plus a sub 2 plus a sub 3 plus, out here, a sub 100 plus a sub 101 plus forever and ever and ever, where a sub 1, a sub 2, a sub 3, etc. are numbers. So I gave you 3 examples, and in these 3 examples, what happened, and I can give you more, there's plenty more. In these 3 examples, we arrive at a place where we get this thing that I'm calling an infinite sum, because it's adding up numbers, but the number of terms in your sum is infinite. And so a generic sort of sum like this would be numbers. I'll call the first number a sub 1. I'll call the second number a sub 2, the third number a sub 3, etc. We need to make a definition of this, but we have to do it in a way that it makes intuitive sense. Now, that's sort of a confusing thing, because most of the stuff we're going to do the remainder of the semester is difficult to learn. These are difficult ideas. And so it seems misleading when I tell you that we're going to define this so that it makes sense, because it's going to be hard for you to learn this stuff. However, what I mean by that is that we can define this thing to be anything we want. I can just say that's cat, that's dog, that's energy drink. I'm just going to define that sum to be iPhone. I can do that. It ain't going to help us, but I could do it. What I want to do is I want to make this definition so that the intuition that comes into play in the 3 previous examples, I want to define this thing so that its definition makes logical sense, but it also makes intuitive sense. Does anybody have a comment or a question? Okay, so that's what our goal is. How do we properly define this? So what we're going to do is we're going to start with a list, and more specifically, an ordered list of numbers. So we're going to have to build our sort of toolbox up to make this definition. Please feel free to ask me any questions at any given time. So here we go. We got to make some definitions. So a sequence, so this is the operative word. A sequence is an ordered list of numbers. We denote this list by, here's a new symbol for you. We take A, and then we have a subscript n, and then we write n equals 1 here, and we write infinity. So now we're introducing to you some new notation. So a sequence is an ordered list of numbers. So this is shorthand for this. So a sequence is a list of numbers, and how we let the reader know that we're talking about some specific order to this list of numbers is we put these braces around it. That tells us that it is a sequence. So why do we use these subscripts? Well, this tells the reader what position in the sequence it is. So you have the first term, the second term, the third term, the 19th term. So we call A sub k the kth term. So the subscript n is called the index. Any letter will do. You can use N, you can use I, you can use J, you can use K. You can use any symbol you want. We typically like to use the letter N. And the reason we like to use the letter N is because notice all the subscripts. If it's an ordered list, then we can count them off, the first, the second, the third. So really, the indexes are all natural numbers. 1, 2, 3, 4, 5, the counting numbers. So we typically use N for that. So if you want to get technical, a sequence is a function with domain, not the real numbers, but the domain is actually the non-negative integers or the natural numbers. So what this means is the following. And again, this is not, when we see examples, it might be a little easier, but we're asking you we're jumping up a level of conceptual difficulty here. So this takes some time. This takes some time to learn. So don't get overwhelmed with all the new I don't want to say information, but mostly what makes this difficult is the notation, where we're throwing a lot at you. So here's two common ways to generate a sequence. The first is what we say explicit. And what does that mean? Well, that means A sub n is defined as some function of the natural numbers. And the second way is what's called a recurrence. And that is the nth term is defined by a function of the previous term. So what number comes before n? The number that comes before n is n minus 1. All right, so this is scary, and we're going to do an example right now, but it is worth noting that while the notation is frightening, once we throw some actual concrete ones at you, it becomes a little less daunting. Note, we can start our sequence at any non-negative integer. Usually, we start with n equals 0 or n equals 1. So that might not be clear right now, but let's do some examples and see what we mean. Okay, so let's look at the one that we've already studied a lot. So the one we were looking at before that we wanted to add up was this guy. We had 1/2, 1/4, 1/8, 1/16, 1/32, etc. How can we generate this sequence? Well, in shorthand, we might write that this is 1 divided by 2 to the power n, where n begins at 1 and goes forever and ever. Because look at all those denominators. Those are just the powers of 2. Let's do another one. It's a little more, maybe easier. How about we do 1, 3, 5, 7, 9. These are the odd numbers, the odd positive integers. How might we describe how this sequence is generated? Well, one way to describe an odd number is to write it like this. We can write them as 2k plus 1, where k starts at 0 and goes forever. So this is going to look scary for us, but let's try to put the pieces together. This is the guy when k equals 0. This is the guy when k equals 1. This is the guy when k equals 2, etc. I mean, plug k in. When you replace k with, say, 2, you get 4 plus 1, which is 5. Let's look at another one. How about we do 1, -1, 1, -1, 1, -1. So it alternates between 1 and -1 forever and ever and ever. How might we generate this? Well, we can take -1 and raise it to, how about the k plus 1 power? And start k from 1 and go to infinity. So when k is 1, you get -1 squared, which is 1. So anytime the exponent's even, we get +1. Anytime the exponent's odd, we get -1. Does anybody have a question or a comment? It should be noted that these three are these guys are generated by an explicit formula. And that explicit formula is the one thing on the right, the 1 over 2n, the 1 or the 2k plus 1. Those are explicit formulas. Any questions, comments? Okay, so let's do one example of a recurrence sequence. Or maybe we'll do two. So let's look at an example of one defined recursively or using a recurrence relationship. So set A1 to 1, and for n greater than 1, define A sub n by n times the previous guy. So let's use this notation. It'll be a little more clear. So the next guy in the list will be defined by n times the previous guy. So let's compute a few. So what's A sub 2? Well, A sub 2 is 2 times A sub 1, which is 2 times 1, which is 2. What's A sub 3? Well, that's 3 times A sub 2, which is 3 times 2, which is 6. And then A sub 4 is 4 times A sub 3, which is 4 times 6, which is 24. You know, and so if you wanted, you can write this out. What's our sequence? It's 2, 6, 24. The next guy would be 120 if you computed it out. So well, I guess we forgot the very first one, which is 1. So the fifth term is 120. What's the sixth term? Well, the sixth term would be 6 times 120. What is 6 times 120? Well, that's 720. So there you go. And we could keep going. So that is a sequence defined recursively. It turns out some of you will get to have lots of fun with recursive sequences because if you take certain math classes and in computer programming, lots of things are done recursively. Okay, so here's the question that we want to sort of ponder, and this is where we're headed. Don't forget, our goal is to really study these infinite sums. That's what we really want to study, and we have to build up the proper machinery to do that, though. So here's our question. What patterns can we recognize for sequences, and are they useful? So if you look at some of these examples, you'll notice certain patterns, and you wonder, okay, are these patterns of any use? And it turns out some are and some aren't. So it's useful to define some terms. So here we go. So we say some arbitrary sequence a sub n is increasing if each term in the sequence is larger than the previous term. So we have increasing. We can also have non-decreasing, which is a slight variation of this. And that is if each term is no smaller than, it could be equal to the previous term. And then we say that you're decreasing if you make each term in the sequence, if it's less than the previous term, we say you're decreasing. And then, of course, we can also do non-increasing. So there's a subtle difference in non-decreasing and increasing. And then we have a couple more terms. We call any sequence a sub n monotonic. If it is either non-increasing or non-decreasing. The sequence is said to be bounded above if there is a number m such that a sub n is less than m for all n. And then similarly, we can define bounded below. And then the very last term we're going to define is if it's bounded above and below, we say it's bounded. So this is a lot of words. It's very overwhelming. I understand that. You don't need to memorize these words. You don't need to make flashcards. What you need to do is work problems out and read examples and study the examples in the book or on the internet and think about these words when you're doing these things. So without worrying too much about these words, let's sort of, think about these things and through an example. So let's go back to the one we've been working on pretty much the whole time. So if we take 1/2, 1/4, 1/8, 1/16, etc., this guy is decreasing. Why? Well, look at the terms. I mean, you could see, you say, okay, 1/8 is bigger than 1/16. I get it. And 1/16 is bigger than 1/32. But how can we show it in general, not just looking at the first few terms? Well, why? Well, a sub n plus 1 is always is always bigger than, I wrote it backwards, is always smaller than the previous term. Why is that true? Well, let's write it out. What is this? This is 1/2 to the n plus 1, and that's clearly smaller than 1/2 to the n. Why is it clearly smaller than that? Well, because you can rewrite that as 1/2 is clearly less than 1. So this is an argument you might not have ever seen this kind of thing before. So you really need to study this example. We can say more though. So it's bounded below by 0. Clearly 1/2 to the n is always bigger than 0. And for full disclosure, it's bounded above by, say, 1. Clearly 1/2 sub n is less than 1, no matter what n is, as long as it's a positive integer. Does anybody have a question about this? Comment?
I had a quick question.
Sure, Paul. What's up?
So, in our definitions for bounding, is it a value? Because in our example with the 1/2, 1/4, 1/8, 1/6,
Yeah.
one would be included, right? If in our sequence that we wrote.
Which one are you talking about? Are you talking about a specific sequence back here?
So this example that's on our screen right now.
Yes, this one. Okay.
Yeah. So bounded below by 0, I get that, because it's it's kind of like the limit that you never quite
Right.
get
Well,
the
we didn't
range of.
define a limit yet. That's where we're going next. But you're right. That's so you have the right. You're on the right track for sure.
Right. So if you, oh, never mind. I answered my own question.
You sure?
Yeah, because I was looking at our definition of the sequence as 1/2 to the n,
Yeah.
and I was thinking, well, what about if n is 0? Because then you would get
Well,
1. But
right.
we
But I
said in our,
didn't include that one here. So here, by context, what we're really doing here is we're just considering n starting at 1. But you wouldn't be wrong if we started it at 0. Then you could still say it's bounded by 1 because you can say it's less than or equal to.
okay, that was
Makes
just
sense?
my. Yep.
And by the way, these bounds aren't unique. I mean, any number bigger than 1 is an upper bound, and any number smaller than 0 is a lower bound. Does that make sense? So they're
Yep.
not unique. And in fact, you might have thought of a different number than I chose. I mean, I'm looking at this hindsight 2020 because, like what your mind is telling you, there's a bigger thing happening here. There's this limit happening, right? And so that's where we need to go next. And so we might as well just throw that at the bottom of here. So note a beautiful pattern is that the terms, when we go far out, so when n is large, let's put that in quotations because that's very subjective. That is, take a term, take like the 100th term. I mean, go to a calculator and compute, the 100th term. I mean, what is a sub 100 is 1/2 to the power 100. I mean, most calculators, let's see what Google gives me. If I do 1 divided by 2 to the 100th power. Yeah, so this is, I mean, Google's, I'm surprised it does round it, but it should have I'm surprised it didn't just say 0. I mean, this is, for all intents and purposes, 0. But what is it approximately? It's 7.8 times 10 to the negative 31. I mean, that number is 0. Do you understand what I'm saying? I mean, if I gave you, if every day I gave you that much of a dollar, 7.8 times 10 to the negative 31 of a dollar, it's going to take you a long time to make money. That's a very small number. Okay, so we know what this kind of pattern is. We've seen it before. So that suggests we make this definition. So there's good news and bad news. We have to make a definition, which is scary. So we say A sub n converges to L if we can make A sub n arbitrarily close to L by choosing n sufficiently large. So the new word here is converges. We've seen this word once with these improper integrals, and it means a very similar thing here. So if this is true, we write the limit as n goes to infinity of A sub n equals L. So this is very familiar notation, and there's a reason that it's familiar, because it's very much connected to what we did in Calc 1 with limits. Okay. If If the sequence does not converge, we say it diverges. Okay, so don't get overwhelmed with this, because really we're defining something new, but it's a special case of something we studied in Calc 2. Excuse me, Calculus 1. So all these things that we learned about in Calc 1, these limit laws and stuff, you got to go back in your time machine and go remember all that crap. But all that stuff we learned in Chapter 2 in Calculus 1, it's all going to come back and be useful to us. So we should be very, very happy about that. So, so let's instead of wasting time, let's say what the sort of the big super useful thing is. I like to call this awesome news. Since a sequence is just a function, the limit laws from Calc 1 carry over. So all the stuff we did in Calc 1, the limit laws, L'Hopital's rule, the squeeze theorem, all that stuff comes back into play. So, for example, just like we saw here in this problem, it is clear to us, if you go and look at the 100th term, the 1000th term, those numbers are zero, right? But our limit laws, we already know that from our limit laws. So let's just write down, I mean, let's not hide the, what do they say, bury the lead, as they say in the news. So let's just look at a couple examples real quick. Most importantly, the one we've been studying, the limit as n goes to infinity of 1 over 2 to the n is just 0. The limit as n goes to infinity of, say, 3n squared plus 5 over 7n squared plus 6. We know that this is, let's say 6n for fun. This is just 3/7. Let's do one that's a little more involved. The limit as n goes to infinity of, say, the sine of n over n. We know by the squeeze theorem in these limits that this has to be less than the limit or equal to the limit as n goes to infinity of 1 over n, because the sign is bounded. And so this is equal to 0. And then if you wanted to, be completely wise with it, is similarly the limit as n goes to infinity of sine of n over n. You can also argue that it's greater than or equal to the limit as n goes to infinity of negative 1 over n, which is also equal to 0. So by the squeeze theorem, the limit as n goes to infinity of sine of n over n is equal to 0. Whew. Anybody have a comment or a question? Now, the next thing we're going to state is mostly a very theoretical tool, but it's extremely important for what we're going to be doing. And that is, if I have a sequence that's always increasing, but it has a ceiling, it's bounded above, well, then it's going to be trapped. And so it's going to have to converge. And similarly, if it's decreasing but bounded below, it's going to converge. And so what we do is we state this as a theorem because it's extremely important. We're not going to prove it though, but it's intuitively clear. A bounded monotonic sequence converges. How we doing, gang? We hanging on? We holding on strong? All right. We're ready now to finally tackle our infinite sum. So we are finally ready to define a sub 1 plus a sub 2 plus a sub 3, our infinite sum. Okay. Gonna start looking at some scary stuff again, so I feel bad for you. I'll take a moment to drink some water. Okay. Given a sequence, a sub n, which of course we know is a sub 1, a sub 2, etc. We call its sum, and I'm going to use the word sum in quotations because it's not really a sum, because it doesn't make sense to add up infinitely many things. So we're using this word in the colloquial way. So we call, it is sum. I got to get my grammar down. Its sum. What is its sum? Its sum is this. It's a sub 1 plus a sub 2 plus a sub 3. And I guess let me be more careful with my words. Let's not say its sum. That sounds silly. Let's say we call the sum of its terms. So what is this? This goes on forever. So how can we write that? Don't forget we have shorthand notation for this. So we call this an infinite series. So it's not called an infinite sum. The correct mathematical term is infinite series. So what does this mean? How do we define it though? If we're just saying it's equal to this, we're calling this thing an infinite series. So you can write it as this extended version with the ellipsis, or you can write it in the sigma notation compactly. We call that an infinite series. What does it mean? Well, it means the following. Okay, we define this. So what is it equal to? What is this thing? This k equals 1 to infinity. Well, by definition, it's the limit as n goes to infinity of this sum. So if you study this for a second, what you'll realize is this series is not adding things up infinitely, because that's impossible, but what it's doing is it's taking a series and creating a new series, taking a sequence and creating a new sequence and studying its sums. So it is useful to denote this guy by S sub n. So for example, what is S sub 1? S sub 1 is just A sub 1. What is S sub 2? Well, that's A sub 1 plus A sub 2. What is S sub 3? That's A sub 1 plus A sub 2 plus A sub 3. Yeah. What is S sub 100? S sub 100 is A sub 1 plus A sub 2 all the way out to A sub 100. So we give these guys a name. We call these, so we call S sub n the nth partial sum. Why is it a partial sum? Because we're only adding up n of them. Maybe 100, maybe 3, maybe 364. Okay, so here's the big put it all together, which is quite still scary. There's a lot going on here. So if this guy converges, we say the series converges. And what do we write? Well, what's the series? The series, let's remind ourselves, is this guy, which by definition, this is the definition, it's this limit. Another way of writing this, if you want it, is you can write it as S sub n. And if this converges, what's its limit? Let's say it's L. So there's a lot happening here. This is a very conceptually difficult thing. When I was in Calc 2 years ago and I had to learn this, I was just as lost as you are right now. It will take an effort on your part to get your handle on all this stuff. Unfortunately, that's just the way it is. This is hard to learn. But what we're going to do now is we're going to go back to our original example and we're going to see how it all works. Okay. Does anybody have a comment or a question? So now we want to investigate this guy again, which we now know we can write more compactly if we wanted to as 1 over 2 to the k. K goes from 1 to infinity. So this is the guy we started the whole day off with. So we want to look at how, using our definition on the previous page, how do we handle this? So how do we study it? Well, by definition, we set S sub n. What is S sub n? Well, that's the sum up to the k, or I'm sorry, of how do I say it? It's the sum for k starts at 1 and goes up to n of 1 over 2 sub k. And what we write is, this is 1/2 plus 1/4 plus 1/8 plus we know it goes all the way up to the nth guy, but what comes before n? So sometimes it's useful to write that. The number that comes before 10 is 9. The number that comes before 100 is 99. The number that comes before 37 is 36. So what comes before n? Well, the number that comes before n in the natural numbers is n minus 1. So what we need to do is we need to take the limit of this. So here's what we have to ask ourselves. We need to know, what is the limit as n goes to infinity of S sub n? Well, if I just go and try to take the limit of that, I'm going to get nowhere. I mean, every time n gets larger, that sum gets bigger. So we have to come up with some magical thing. We have to use our brains to somehow rewrite this and get some information. Does anybody have a comment or a question? Okay, let me repeat this because this is scary the first time you see it, because it seems like it's some magical thing. That expression I have right now has n terms in it. I don't have any limit laws or any ways of taking limits that's going to help me with that. So what I have to do is I have to get creative, and I have to figure out a way to rewrite that so that I can use my limit, the stuff I know about limits. Okay, so here's a thing that's going to seem like magic, but it's not really magic, provided you've seen it before. And you got to maybe gain some intuition for it. And it's a trick that doesn't just work once. It works in lots of places. So we don't really call it a magic trick. We call it a useful technique. But keeping that in mind, what I'm about to do is going to seem like it comes out of left field. Although in hindsight, you'll say, wow, I didn't think of that. Okay, so here's what we're going to do. I am going to take this thing, and I am going to try to, instead of writing it as n terms, I want to write it as something compactly. So one way to do this is, and this is a theme that has popped up many times, you just don't really think about it, is I'm going to take S sub n, and I'm going to write it in two different ways. And then when I write it in two different ways, I'm going to either add them or subtract them. And when that happens, oftentimes lots of excess stuff disappears. So again, I am going to write S sub n in two ways. Now you might say, what do you mean two ways? Well, hell, if I said to you, take the number 10, write it in two ways. You can write 10 as 5 plus 5. You can write 10 as 20 divided by 2. You can write 10 as 13 minus 3. You can write 10 in all kinds of different ways. So what I'm suggesting is we can take this scary looking thing and we can write it in a few different ways and then manipulate those ways. And then hopefully things will fall apart, or I guess a better way of saying that, hopefully things will fall into our favor. So here we go. Uh-oh, someone's chiming in. What do we have? This is true. Okay, so we're going to compute S sub n minus 1/2 times S sub n. Now again, at first glance, you're going to say, why did you put a 1/2 in front of that? And the reason is because it is something that is going to, yeah, okay, so when you were a kid and you learned fractions and you learned how to add them at the first time, when they had different denominators, you had them find a common denominator. And there's lots of different ways for teachers to teach you how to do that. And then there's lots of different ways that you could have memorized how to do it so that you were able to do well on exams. Now, some of you are like, I couldn't do that. It was hard. The point is that there was a, you know, before you were taught how to do that, there's no really way for us to think that you would ever come up with it. Someone has to show you this sort of, this ingenious at the time idea. And that's similar to what's happening here. Why am I putting 1/2 here? Well, once we do the next step, hopefully it's clear. So what is this? What is this equal to? Well, S sub n we know is 1/2 plus 1/4 plus 1/8, and then it's plus 1/2 to the n minus 1 plus 1/2 to the n. And then I'm going to subtract 1/2 times the same thing. Now, that looks like a big hot mess to you right now. And I understand that, and I empathize with you because it was scary to me when I learned this years ago. But what I'm going to do now is I'm going to distribute this 1/2 to all the pieces. And when I do that, look what happens. The 1/2 becomes a 1/4. The 1/4 times 1/2 becomes 1/8. So look what happens here. What happens is that if I take my red pen, this term right here, this 1/2 stays, this 1/4 and this new 1/4 go away. The 1/8 minus the 1/8 go away. So let's write down on the next page what all this means. So this equals 1/2 plus 1/4 plus 1/8 plus dot, 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 plus 1/2 to the power n minus 1 plus 1/2 to the n. Let me fix this. Now, what am I subtracting? Downstairs, I'm left with a minus 1/4, minus 1/8, minus all the in-between terms. Now, this will become 1/2 to the n, and then the last term will be 1/2 to the n plus 1. So, unfortunately, we're on two separate pages. I really hope that you'll write this out on your own and convince yourself that it's true. And the thing to note is everybody has a dancing partner to cancel out with, except the very first and the very last terms. All that remains is 1/2 minus 1/2 to the n plus 1. So let's say this again. What we found is S sub n minus 1/2 S sub n is equal to 1/2 minus 1/2 to the power n plus 1. Which you can rewrite. You can rewrite as S sub n is equal, multiply both sides by 2, and you're left with this. You should convince yourself that this is indeed true. Just do the algebra. Does anybody have a question about that? All right, so what have we done? Here's what we've shown. Let's summarize this, because this is actually quite interesting. What we've done is we've shown that the limit, or excuse me, let me write it the other way so it's a little more intuitive. Here's what we showed. We've shown that 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... We showed this by definition is the limit as n goes to infinity of S sub n. So what does that really mean? Well, that means the limit as n goes to infinity of 1/2 plus 1/4 plus all the way out to 1/2 to the n. But this formula we just showed is 1 minus 1/2 to the power n. And this is a very easy limit to compute. It's just 1 minus 0, which is 1, just like our intuition tells us it should be. Go ahead and spend an hour adding all those numbers up. The further you go out, the closer you're going to get to 1. Just like if you go back and try to walk to the wall half the distance at a time. Does anybody have a question about this? Now, this is not going to be easy. You're not going to wake up tomorrow and understand this. I highly doubt it. Well, maybe you will. Maybe you spend a lot of time tonight doing it. In general, this is challenging to do. All right, so the last thing I'm going to leave us with is we can mimic this argument. Right, so okay, so Tommy, you're asking a great question. There's going to be no need to do that. You could, and if I give you more problems and you did it again and you did it correctly, you say, oh my God, there's a pattern here. And you can mimic this pattern. And so what we've done is we've done more. And I'm out of whiteboard, so I have to unfortunately put it up here, because they only give me 20 whiteboards. because they don't want you to be too bored with me. So here's what we learned for in short. If we modify this argument, and it's in the book if you want to see it, but we just did it in a special case. So if you want to learn it in general, you can. But in general, this argument can be modified to prove or to show the following. So let me erase this. I apologize for, I feel like we're everywhere on this. Let me sort of isolate this. Like this. So here's what we can prove. If some number r, whatever it is between 1 and -1, then this series, k goes from 1 to infinity of r to the power k. So these guys have a special name. And so in our problem that we just did, r was 1/2. But we can show this guy, which is r plus r squared plus r cubed plus ... This guy is actually equal to r divided by 1 minus r. So replace r with 2, and you'll see that. You get 1/2 over 1/2, which is 1. So Tommy, to answer your question, no, you don't ever have to do this again unless you want to teach it to yourself. Now you can rely on this formula. Although I would encourage you to try to do it yourself. So these are called geometric series. And they have a very simple pattern. So the good news is they're simple. The bad news is most series aren't. That's what we're going to talk about on Tuesday. Does that answer your question, Tommy? I don't know if it does. I hope it does. So the trick is, if you wanted to prove this general formula that I have in pink, what you would do is you would do everything we did in the previous one, but you replace all the r or all the 1/2s with r. And if you replace all the 1/2s with r, you'll get the same result. So this is a very powerful tool. These geometric series are very useful. They pop up in many applications, and they're used to answer questions about other things. And we'll learn all about that on Thursday. Now notice, if r is bigger, if you tried to like add up 4 plus 16 plus 64, we don't expect that to converge, so we don't expect there to be a formula for it. We expect it to diverge. So again, this is called, these are called geometric series. So and you should know that formula. Now, I wouldn't memorize it. I would do problems, and I'm going to give you problems to do. And when you do them, you're like, oh, okay, cool. All right, any comments, questions? All right, gang, I will leave it at that. I'm going to post an assignment for you. Hopefully you'll work on this stuff. 2 things to keep in mind. Most importantly, we threw a lot at you today. And so I encourage you to get on it right away. And if you have questions, reach out to me. And if I don't respond to the email within an hour, send the email again and then send it again, particularly if it's a question about a problem. And also, feel free to blow me up and remind me to update the rest of your grades. I know some of them are up and most of yours are not. And so you know, squeaky wheel gets oiled, as they say, as it thunders outside. All right, you guys have any other questions, comments, concerns? All right, well, listen, I'll post some assignments. Please start working on them. Thank you guys very much, and I will talk to you Thursday. All right, take care.